right, great. Hi, everyone. I'm Lillian Naimie. I'm a PhD candidate at Colorado State University, working with Jeff Collett, who's in the audience today. And I'm not sure if this was intentional, but the timing with my presentation and the one prior works out really well because I'm going to talk to you a little bit about the atmospheric deposition of nutrients that can lead to some biological growth in freshwater bodies. So specifically, what I'm going to talk to you about today is agricultural emissions, and in particular, emissions of atmospheric ammonia, which you can see in this. And as you watch it play through each year, you're seeing monthly data from EASI, a satellite retrieval of ammonia. Those bright yellow colors are higher concentrations. Those darker colors are lower concentrations. And what you can see here is that we have a strong seasonal cycle of ammonia, but also that some of these agricultural regions really jump out at you. So the Corn Belt through the central US and some other areas that I'll talk about in a little more detail as we move on. So specifically, why are we talking about agriculture? You're probably familiar that the global population has greatly increased in the last number of decades and prior to that. With that, we've had this added need for increased agricultural production, and that's been largely made possible through the advent of synthetic fertilizers, which allow for us to grow many, many more crops in a similar spatial area. And this is some data from the UN for population and then the USDA for agricultural production, corrected for inflation, so we're comparing apples to apples. And when we think about that increasing agricultural production, it really is both crop production and also animals, particularly in these confined animal feedlot operations. Again, largely made popular from synthetic fertilizer application, which you can see an image of here, where they're actually injecting the fertilizer into the plot area. And what you can see on that little tank, hopefully you can read it, is that this particular fertilizer is anhydrous ammonia, and ammonia is the species we're specifically going to talk about today because of its atmospheric implications and frequency that it's used as a fertilizer. So we're applying this to the fields. How does it get into the atmosphere? It's a volatile compound, which means that as we apply these fertilizers, we volatilize some of it back into the atmosphere. When we're thinking about animal production, we have it volatilized from the production of the crops that feed the animals, and then also from animal waste further down the line. Okay, so now I've told you we're going to be talking about ammonia. Maybe you're not so familiar with ammonia. Why should you care about ammonia? We're going to get to that in a moment. 80% of it comes from agricultural activities, and then we also have emissions from wildfire smoke and urban impacts. Now we're going to talk about why you should care about ammonia. So we have ground-based emissions of ammonia gas here in that yellow, and then when it mixes with these precursor emissions, we get particle formation. These particles you should care about because they're small enough that when you inhale, they can make it through your respiratory system down into the depths of your lungs, where they can put things straight into your bloodstream, but also cause damage just generally to your lungs. If you've ever breathed in sitting by a fire outside and your lungs kind of hurt, that's because you're breathing these really fine particles into your lungs. The other reason we should care about it is because of this reactive nitrogen deposition question. So when we have gas phase ammonia, NH3, and then the corresponding particles created, NH4+, they can be deposited to the ecosystem, both to plant life and also fresh water. And once deposited, we can lead to things like acidification, algae blooms, unfortunately aquatic species death, like I'm showing here with this fish, and other deleterious effects. This is particularly important at high altitude ecosystems, which generally developed under nutrient restricted conditions. So when we add additional nitrogen, we have more of a potential for these things to have an impact. And you can see those high elevation areas in the western US, which is going to be the focus of the rest of the data that I show you, both because we have these Rocky Mountain areas that developed under nutrient deprived conditions, And also because in this region, we've seen increased wildfire smoke. I won't have time to talk so much about the wildfire smoke today, but I encourage you to talk to me about it after or come to my poster. The other thing about this region, you can see in those hashed areas, is that we have national parks, which are protected ecosystems, and we really don't want to see algae blooms and plant death in these areas that we're supposed to be protecting. So we're going to use satellite data. Probably you're familiar with a little bit of satellite data, but in case you aren't, the rest of this talk is going to use cross-track infrared sounder data from NASA. And so how these satellites work is that as they orbit Earth, they view some portion of the Earth's surface. As the satellite passes over, it retrieves these pixels. For the CRIS satellite, these are about 14 kilometer in diameter, not particularly fine resolution. But if we stack many of these days of retrievals together, we can do a process called physical oversampling to get to a much finer spatial resolution. And that's what two of my colleagues, Mike Iacono and Kimberly Corwin, have done with this CRIS data to get us to 2 kilometer spatial resolution, which is really important for some of the spatial analysis that we're going to do, because the resolution can really impact what our data results look like. So after a whole lot of work that I've simplified into a schematic slide, we end up with annual warm season retrievals of ammonia. We're focusing on the warm season here, March to October, because it's peak ammonia emissions and also because it's peak wildfire season in the region. So what you can see in this plot on the left are those annual warm season values. And what you can key in on here is that there are 2 regions close to that Rocky Mountain area that really jump out as high concentrations. This is the Snake River Valley in Idaho and an agricultural area in northeast Colorado, both of which are predominantly confined animal feedlot operations, some crop production, but we're seeing a lot of animal-based emissions in those 2 areas. So taking this 11 years of data that we have, the first question we wanted to ask is, how is ammonia increasing and how is that different spatially across the area? So in this other plot in red, those red values are increasing ammonia concentrations, those blue values are decreasing, and what we see again here is that those strongest increases seem to be occurring in these agricultural regions of interest. And to give you a sort of number to think about, those are on the order of 2 to 5% per year, which is a pretty strong increase when we think about even just 11 years of data. So the next thing that we wanted to understand, thinking about these agricultural areas, is how is the spatial area that's being impacted changing? So how's the footprint of those air quality concerns that we've talked about going to change through the data record, and what do we maybe need to be aware of? And so what you can see here is each year of that spatial footprint assessed to show these ammonia hotspot areas. And we can zoom in again to those 2 areas. It's a little hard to see with the whole map. So we can zoom in to the Snake River Valley and also northeast Colorado. And what we see in the beginning of the data record, those dark blue values, is that the contours seem to be more fragmented and to cover up a smaller spatial area. Whereas as we move later into the data record, it looks as though we're seeing bigger spatial areas and more continuous contours. And when we look at that in terms of a timeline and actually determine whether there's a statistically significant trend, that does seem to be the case. So first, for the Snake River Valley, here as we're moving through the years, it's just hotspot area in terms of square kilometers. And so what we see in Idaho is that the spatial footprint of these agricultural hotspots has increased by about 6% per year for the last 11 years. And moving into northeast Colorado, we're seeing a pretty profound increase of 15% per year, looking at this spatial impact area of these agricultural hotspots. And this is really important because we want, again, to understand how this is changing in terms of where is being affected by these highest emissions of agriculture and what we might expect to continue to change for the air quality impacts of agricultural regions. And so with that, I'll leave you with these contours again. And encourage you to come find me at my poster or talk to me after this talk, especially if you're interested in getting into more of the nitty-gritty of this data analysis or talking a little bit about how wildfire smoke is impacting these changes as well. Thank you.